All right. So problem 2 is worded like this. If you have your exam with you, you may read how many independent measurements or how many independent random measurements of a time dependent acceleration signal obtained from a vibrating vehicle under fixed operating conditions would lead to a confidence interval of plus minus 0.5 g. So confidence interval is given as plus minus 0.5 multiplied by g about the mean. If the standard deviation is expected to be, if the standard deviation of the signal is expected to be 1g, standard deviation of the signal is expected to be 1g or just g. So they are saying the mean value plus minus ci. Okay, whatever your mean value is, it's going to be some number, and since g is the convenient scale for expressing these, we call them half a g, 1g. It's like a dozen, half a dozen, 3 dozens. Instead of using actual units, we are just calling it half a g or 1g. Okay. And what do we know about confidence interval? Some number expressed as a multiple of g or in units of g. So one thing you should understand is that the actual value of g, which is the acceleration due to gravity, is irrelevant. You don't need to know the actual value, whether g is 9.8 or 10, doesn't matter, because we write ci is equal to t statistic multiplied by sigma divided by square root of n. So ci is given as 0.5 times g. And sigma is given as 1 times g or just g. So whatever g value is, it's not going to matter. So the question now is, what value of n should you choose so that 0.5 multiplied by the t statistic evaluated at p, which wasn't mentioned in the problem, which you are welcome to choose whatever you want, say 95% at nu equal to n minus 1 divided by square root of n. This equality is not exactly true, but at least approximately true. That is the question. Is that what most of you all understood when you read the question? That is, this term here, t divided by square root of n, needs to be approximately 0.5. That is what is saying about 0.5 or plus or minus 0.5 g. What happens if you make a lot of measurements? Think intuitively. The right hand side will become a way, you can make the right hand side can be made as small as needed by making n large. Would you agree? You make more measurements, this ratio will keep going down. Yeah? It's like asking, I don't want it to be too small. I'm okay with accepting 0.5. What value of n should I choose? That's the question. And if you look at t, if you look at your table for t, okay, you have t95 as a function of nu provided to you from 1, 2, 3, and so on up to, let's say, up to 30. Okay, so this problem requires you to think a little bit intuitively. Look at the range between, say, 10 and 20. Between nu 10 and 20, t varies between what? T varies between roughly 2.2 to 2.0, 2.2 and 2.0. What divided by 2 or 2 divided by what number will give you 0.5 roughly? 2 divided by x is 0.5. What is x? X should be 4, right? Roughly. Which means whatever your square root of n is, it should be approximately 4, or to start with, n should be a number around 16. Okay. So this implies square root of n should be 4, which means n should approximately be 16. Or if you get to 16, I gave credit for people who wrote 16, 17, 18, even 20. It's about hitting the ballpark, not exactly a particular value. So for example, if you try 16, what will you get? So for n equals 16, you get t statistic to be 2.120 divided by square root of 16. So this is 2.120 divided by 4, or this is 0.503. I accept 16. Okay. If you did say, for example, n equals 18, you get 2.101 divided by square root of 18, which if you do, can anyone tell me the answer? Can you punch this in your calculator? 0.495? Yeah. 0.495. Perfect. We are under our 0.5 threshold. So 18 is a great choice. 16 is not bad. 18 or higher will satisfy that condition. So if you are the engineer designing these measurements, you would write a preliminary report saying at least 18 measurements are needed if the confidence interval has to be 0.5 G. That's how you think about it. Is it now making sense? Still not clear? Yeah. Is it now making better?
Yeah, it makes sense. It's just like when I was studying, it's just like different.
Here's the kicker. This problem, I didn't come up with it. It's in the handout, the end of the chapter that I posted. So if you had done practice problems from the chapter, you would have got this. So it's not something I just made up for the exam. It was there in front of you. Practice was the only thing needed. Okay. So obviously statistics it can be a little tricky. I would definitely ask you to, keep working on it. Near the end of the semester, I intend to spend one additional session where I can provide you basically a short list of topics that are going to be there on the final and give you exactly problems to try and prepare for it. Okay. What other difficulties were there? Anything that you want to ask? To give this back to you. If something comes up, please let me know. And those who have lower scores, please come and talk to me. Let's figure out what we can do better to help you improve. Okay. All is not lost. There is still the makeup final that can replace both your exam 1 and 2. So please work hard and let's catch up. Okay. Can I erase this? Anybody writing? So we come to the most, I don't know, not my favorite topic, interpolation. What do you know about interpolation? Have you heard the word before? I'm sure if you have taken a thermodynamics class, at least the mechanical engineers, you would have done interpolation. Can you tell me what is it?
When you're values given to find the value in between two x and y is given.
That is not just linear interpolation, that is interpolation. What is linear interpolation? So if you have a set of discrete values, like a table, say for example, if you have a function which we'll call y equal to f of x, and you have it known at specific number of points, but I am interested in a particular value which is not part of my database. So there is x1, x2, x3, x4, and so on. I am interested in x0, which is not part of my list. How do I get that? So interpolation is the process of computing values between points at which data was collected, at which the original data was collected or obtained. So if I have 2 points, okay, I want to know this, let's say this is x1 and y1, and this is x2 and y2. I wish to know the value of y at say some x0, which is between x2 and x1. How would I do this? That is the question. Okay. The whatever process that is providing this data, the real process may or may not be linear. That is, if you had data and suppose you connected 2 points and you just drew a straight line, there is no guarantee that this straight line will contain all the other data points in your set. Okay, that is why we try to do interpolation. Interpolation is done for reasonably narrow ranges between data points. So when we say x1 and x2, we assume implicitly that they are reasonably close together. So if we want to get f of x0, assuming x1 and x2 form a straight line, how do you do that? How do you fit a straight line between 2 points? This is a concept you might have learned in prior calculus, or yeah, I'm sure calculus 1 or 2. So if I were to draw a straight line between them, what is the equation for this straight line? No, there is no squared here. This is linear equation, right? So let's say we want some arbitrary point. We'll call it x0, and at that point, let's say the value is y0. Just write the expression for the slope. What is the slope of the slope of this line connecting the 2 points? y2 minus y1 divided by x2 minus x1. That is the slope, right? Right? Slope. So here is the slope m, which is y2 minus y1 divided by x2 minus x1. If you are here at this point x1, okay, you are here at this point x1, and you want to go to this point x0, okay, what is this distance? This distance is x0 minus x1. This distance is x0 minus x1. This slope is m. Okay. Then how do I compute this y0 if I know y1? That is the question. You can do trigonometry, can't you? So y0 minus y1 divided by x0 minus x1. What is this? Opposite by adjacent. Sorry? No. Tangent. So this is tangent of theta, if I call this angle theta, which is nothing but m, the slope. And you do know that the slope is approximated using the 2 points, which is y2 minus y1 divided by x2 minus x1. This train of thought is making sense to you. That is, you are just taking any point between the 2 points, writing their distance and the slope, and using that you are evaluating what is this height. Okay, so you can write y0 minus y1 is equal to y2 minus y1 divided by x2 minus x1 times x0 minus x1. or y naught equal to y1 plus slope times distance along the x direction. Okay, so this is the formula for linear interpolation. Let's do an example right now to kind of use it. Okay. All right, problem 18.6 from the text. Can I erase the left side? Problem 18.6 from the text, which is x, f of x, 1, 3, 2, 6, 3, 19, 5, 99, 7, 91, 8, 4, 4, 4. For this table of data, you can obviously see 1, 2, 3, 5, 7, 8. Not every value is there, obviously. We would like to evaluate f of 4, which isn't on the list. So 4 obviously lies between 3 and 5. So we would say f of 4, if you want to know, you would base it on x equal to 3 and x equal to 5. So you can say x1 in this formula here, x1 is 3, x2 is 5, f of x1 given as 19, f of x2 given as 99, and x naught that we are interested is 4, and we are interested in f of x naught. This is the task or calculation to do. Use this formula, f of x naught equal to f of x1 plus slope. What is the slope here? F of x2 minus f of x1 divided by x2 minus x1 times x naught minus x1. So that would be f of x1 is 19 plus slope is 99 minus 19 divided by 5 minus 3 times 4 minus 3. This 80 divided by 2 is 40, 19 plus 40 is 59. So f of 4 would be 59. Okay. When is this linear interpolation a reasonable thing to do? Is this a reasonable call to call this variation between 3 and 5 to be linear and getting f of 4 equal to 59? How do you check whether what you did is correct or not? Your data looks like this, as opposed to your data looking like this. Okay, by thinking it is a linear by doing linear interpolation, what you are assuming is that the function connecting these 2 points, whatever in reality it might be, let's say in reality, it looks something like this. In reality, let's say it looks something like this. Okay. By assuming linear interpolation, whatever reality is, you are assuming it just connects with a straight line. That's what interpolation means. Neglecting all the complexity that may exist between point 1 and 2 to just think the trend line is only linear. When is that okay and when is that not okay? That is my question for you. When is it okay? Look at this data set. If I tell you that the function that is underneath this data set is actually a straight line that just runs like this. So I'd say this blue line is truth or true value of the function, true form of the function, and the black circle and the x's, they are discrete data points. When is it, in this case, is it okay to consider the variation, doing linear interpolation? In this case, second case with the x's. In the x's case, if I assume that there is a straight line connecting them, I'm pretty much correct about it because the true data is also linear. Okay, so how do you check if a given data is linear or non-linear? Plot it and look at the slope or changing slope, right? So you can either plot it and see if it follows a straight line with a constant slope, or mathematically you can just check what is the slope at different points. Just consider this. For a difference of 1 unit, there is a change in 3 units. For a difference of 1 unit, there is a huge change, nearly 150 units. How is this data linear? Of course, it is not linear, right? So this data or this case is actually a bad application of linear fitting between even these two. Look here. For a jump of 2 units, there is a jump of 80 units. For a jump of 2 units, there is a jump of nearly 200 units. So this is not clearly linear data, but we still use this to apply or try the linear interpolation formula. So if it is not linear data, what is the next best thing we could do? Instead of considering, so if I'm interested in, say, this is 1, 2, 3, and then 5, and I was interested in 4, okay, what is the next best thing you can think of? Forget the textbook. If you see it, they'll tell you an answer. If you're trying to approximate a curve, linear is the simplest approximation you can make. Because if I write y equal to, let's say, a0 plus a1x. Okay, the true function or the true representation of this function could be a0 plus a1x plus a2x squared plus a3x cubed plus and so on up to infinity. I'll give you one example. You know the function e power x, right? How do you represent that as a power series? E power x is actually 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial plus x4 to the 4 factorial plus and so on up to infinity. If I just choose a linear equation 1 plus x will still describe e power x up to a distance, up to a value of x, after which the higher order terms will start becoming important. So a linear is the simplest approximation. The next best approximation will be quadratic. If I include one more term, the a polynomial 1 plus x squared over 2 factorial is still a pretty good representation of e power x if I don't take x too high. As I make x higher and higher, you need to include more and more higher order terms. Okay. So for the same problem, evaluating f of 4, we did linear interpolation, and we got a value of f of 4 equal to 59. Shall we now learn quadratic interpolation and try to get the same thing again? Like try a better approximation of this. Okay. Making sense? I see stone cold silence. Maybe the exam scores are in your head. It will get better, I promise. Okay, so all right, we're almost about time. We'll probably continue this on Monday. So if I have 3 points, okay, if I have, for example, 3 and 5, and I have f of 3 and f of 5. What is f of 3? 19, and f of 5 is 99. Okay. The true variation between these 2 points could be something like this. I don't know. I don't know the truth. You can't know the truth with only discrete data. So if I were to fit a quadratic to these 2 points, would that be possible? Can I fit a quadratic with only 2 points? What is a quadratic function? It has to have 3 coefficients, a0, a1 and a2, so that if you had 3 points, which could include let's say the first also the point 2, where you have 6. If you had 3 points, you can fit a parabola. Need 3 points. Okay, so here is 4. Here is 4. So to get 4, I can choose as my stencil involving 2, 3, and 5. So I can write y equal to a0 plus a1x plus a2x squared, and I can use the 3 points here. So let's say I use 2. So this is a0 plus 2a1 plus 4a2 equal to 6. And then for 3, I have a0 plus 3a1 plus 9a2 equal to 19, and a0 plus 5a1 plus 25a2 equal to 99. You can write 3 equations in 3 unknowns if you have a stencil that contains 3 points to get a0, a1, and a2. One more minute, let's stop. Okay. So if you get a0, a1, and a2, then you could put this back in here to get f of 4 as a0 plus a1 times 4 plus a2 times 16. So that you will get a slightly better approximation of f of 4 than the linear. Okay. Last point for the day. I chose 2, 3, 5, right, as my stencil. I could have also chose 3, 5, 7. There are 2 choices here. Instead of choosing 1, 2, 3, and 5, which contains 4, 3, 5, 7 also contains, right? Anything higher won't contain 4. 5, 7, 8 won't contain 4, or 1, 2, 3 won't contain 4. So the other stencil possible is 3, 5, 7. And you could repeat the same process using the other stencil. You will get a f of 4 value. So which value to pick? Which stencil is the holier cow? is this the correct way to pick, or is this the correct way to pick? What reasoning would you think to say something is better than the other?
5 sevens that are dispersed, evenly dispersed.
It's evenly dispersed, okay,
2, 3, 5.
okay, okay, that is one way to think about it. What if you had two stencils which are equal, both dispersed in the same way?
I assume. The 3 to 7 have more covers, more values than 2 to 5.
Actually, the opposite. The one with the narrower range is always the better approximation, because as you stretch your range, the chance of you getting this wrong increases. So you got it just backwards, okay? But good, you're thinking. Let's continue this on the next class, okay? Thank you.